All right, let's dive into something you probably never thought would be all that interesting. Ready? It's train rails.
The reels themselves?
Yeah. So we've got some excerpts here from a technical document all about railway engineering and how those things are made. And trust me, it's way cooler than it sounds.
It's pretty amazing how much goes into something that seems so simple, right? I mean, at first glance, it's just steel beams.
Exactly. But they're holding up tons of metal, rumbling over them every single day. So how do they work? Well, that's what we're diving into today.
And it all starts with the design.
Okay, so like with those grooved rails you still see on tram lines and stuff, pretty basic concept, right?
Yeah.
The groove guides the wheel.
Absolutely. Simple, practical, perfect when you want the tracks to blend into the road, like in a city.
Right. But then you have that bullhead rail. Now that's a name that sounds heavy duty.
It does, doesn't it? That's the one that looks kind of like a mushroom if you picture it in profile.
Okay, yeah.
Victorian engineers, brilliant as they were in many ways, came up with that design.
Oh, so it's an old idea.
What?
What was the thinking there?
Well, they figured when one side of the rail gets worn down, you just flip the whole thing over, instant fresh rail.
Oh, smart. In theory. Except I'm guessing it didn't quite work out like that.
You got it wore down on both sides, back to the drawing board.
Makes sense. So that's where the flat bottom rail comes in, right?
Exactly. The Vignol's rail, the one you see almost everywhere today.
The MVP of the rail world.
Mm.
But what made it such a game changer? Why was that one so much better?
It's all about those fish plates, the metal plates they use to bolt sections of rail together. That flat bottom design was perfect for that, made for a much smoother, more continuous track.
And smoother means faster,
Yeah.
right? Less bumpy, too, I bet.
Exactly. And smoother, more continuous track, that paved the way for even more innovation, like continuous welded rail. But we'll get to that a little later.
Okay, teasing. But before we move on, let's break down these flat bottom rails a bit more. The document mentioned all these different UIC profiles, UIC 54, UIC 60. It's like a secret code.
Not a secret code exactly, but it is a standardized system. The UIC, that's the International Union of Railways, they came up with it to classify the different types of rail profiles.
So it's all about shape and size and what each profile can handle.
You got it. They wouldn't want, a massive freight train running on a rail designed for a little commuter line. Different rails for different jobs.
Okay, that makes sense. So how do they even make these things strong enough to handle all that weight and stress? Is it like a giant blacksmith situation?
Laughs. I wish. It's way more high-tech than you'd think. Huge furnaces, carefully controlled temperatures, this process called continuous casting.
Continuous casting. Okay, that does sound pretty intense.
Molten steel gets poured into a mold, but the mold's constantly moving, shaping the steel into this long, continuous rail. No room for error because even a tiny weakness in the steel, disaster.
High stakes. So how do they make sure there are no hidden flaws?
They use some pretty amazing technology for that, stuff like Foucault currents.
Foucault currents.
Basically, they're spanning the entire rail with these currents that can detect the tiniest little cracks or impurities, things you'd never see with the naked eye.
Wow. It's like giving each rail a super-powered X-ray or something.
Exactly.
But okay, let's talk about what the rail's actually made of. What's in that steel recipe that makes it so incredibly strong?
It all comes down to chemistry.
Oh boy, here comes the science part.
Oh, laughs. Don't worry, it's not too complicated. Think of it like baking a cake. You need the right ingredients in the right amounts. Too much of this, not enough of that. Your cake is ruined. With steel, it's the same idea. But instead of flour and sugar, we're talking carbon, manganese, silicon, elements like that.
Okay, so what are the key ingredients? What makes a super rail?
Well, you gotta have carbon. The more carbon you add, the harder the steel gets, which is great for wear and tear. But here's the catch.
There's always a catch, isn't there?
If you add too much carbon, the steel gets brittle, like a dry twig. It might be super hard, but it'll snap under pressure.
So it's a balancing act.
Exactly. And that's where manganese comes in.
Manganese.
Manganese increases the ductility. That means it can bend without breaking. And that's what lets those rails handle the constant stress of trains rolling over them day after day.
So it's all about flexibility.
Exactly. And we can't forget chromium and silicon smaller amounts, but they're crucial for wear resistance.
Which, when you're talking about train wheels grinding against the rails.
Super important. Here's where it gets really interesting. It's not just the individual elements, it's how they interact. The document mentions something called equivalent carbon percentage, basically meaning that the overall properties of the steel depend on the whole recipe, not just the individual parts.
It's like a gourmet meal for a train track.
Laughs. And speaking of gourmet, the shape of the rail itself is just as important as the material. But we'll get into that next time.
So we've got these precisely engineered rails crafted from a secret recipe of steel.
But what kind of forces are we talking about here? What are these things actually up against?
Well, imagine the weight of a fully loaded train car. Now imagine all that weight concentrated on those tiny contact points where the wheel meets the rail.
Okay, yeah, that's got to be a lot of pressure. But it's not just the weight, right? Because the train's moving, speeding up, slowing down. Exactly. And don't forget about curves. All those actions create enormous stresses and strains on the rails.
I'm starting to see why they need a whole engineering document just to explain this stuff. So how do they even measure those forces? Like, what are we even talking about here?
Well, one word, Hertz. Hertz stresses.
Hertz. Okay.
It's named after the physicist who figured out how to calculate the pressure between curved surfaces, like, say, a train wheel on a rail.
Okay, so it's named after someone. That makes it sound a little less intimidating.
Yeah.
But still, give me a real-world example here.
Okay, imagine you're biting into a piece of hard candy and it cracks.
Ouch. Been there.
That's Hertz stress in action. Now multiply that by, a few thousand, and you've got a sense of what those rails experience every time a train rolls over them.
Yikes. And they have to make sure the rails can withstand that kind of force thousands, millions of times over their lifespan.
Exactly. And it's not just about that initial impact either. Remember, we were talking about fatigue earlier.
Right, like bending a paperclip back and forth until it breaks. Eventually, those tiny stresses add up.
Precisely. Metal gets tired too, you see. And those microscopic flaws that can exist even in the most perfect-looking steel, those become weak points.
Like little cracks just waiting to grow bigger.
And here's where it gets really interesting. It's not always the surface of the rail that takes the biggest beating.
Really, you'd think that's where all the action is.
You'd think so, right? But a researcher named Dang Van, he figured out that the maximum shear stress, the kind that really drives fatigue, often happens just below the surface, where those stress weights kind of converge.
So it's like a hidden weak point.
In a way, yes. And that's why understanding these stress patterns is so important when designing rails. It's not just about making them strong, it's about making sure they're strong in the right places, anticipating where those weaknesses might develop over time.
That makes sense.
Yeah.
And I'm guessing there are other things that can go wrong besides fatigue, right? What about those rail defects the document mentioned?
Oh, yeah. There's a whole catalog of potential rail defects, each with their own charming name and everything.
Yeah.
The UIC, they even have a 4-digit classification system for them.
4 digits. Wow, that's serious business.
Yeah.
But let's not get bogged down in codes. Give me some examples. What are some of these defects?
Okay, well, a common one is longitudinal vertical cracking. Pretty self-explanatory. It's a crack that runs along the length of the rail.
Yeah, I can see how that wouldn't be a good thing.
Definitely not something you want to see on a high-speed line. And then there's the more exotically named tache ovale, which basically means there's an internal flaw that can grow and eventually reach the surface.
Tache oval?
Yeah.
Sounds kind of fancy for something that could cause a train to derail.
Right. But yeah, these things can start small, maybe even during the manufacturing process. But over time, those constant stresses can make them grow and weaken the rail.
So how do they even find these hidden dangers? Is it like some kind of metal detector for train tracks?
Well, they still do visual inspections, of course, but they've got some pretty high-tech tools, too. Ultrasonic testing, for example.
Ultrasonic. So they're basically giving the rails a sonogram.
Exactly. They send sound waves through the steel and look for any irregularities that might indicate a flaw. It's like seeing inside the rail without having to cut it open.
That's amazing. I had no idea. So much went into something we usually just take for granted. Speaking of things we take for granted, continuous welded rail. CWR.
Ah, yes. The holy grail of smooth train travel.
The document made it sound like a pretty big deal. No more clippity-clack, huh?
Exactly. With CWR, they actually weld the rails together, creating one long, continuous track that can stretch for miles and miles. No more gaps, no more clickety-clack, just a smooth, quiet ride.
Okay, yeah, I can see why that's the holy grail.
Yeah.
But why wasn't it always like this? Why did it take so long to make it happen?
Think about it. You've got this long, continuous rail sitting out in the sun all day. What happens?
It gets hot, so.
Steel expands when it gets hot. With the old-fashioned jointed tracks, the gaps between those sections of rail allowed for some expansion and contraction. But with CWR, all that expansion has nowhere to go and buckle.
Ah, okay, I hadn't thought about that. So how did they solve it?
They came up with special elastic fastenings. These things could hold the rails securely while still allowing for some movement.
Elastic fastenings.
Yeah.
Like giant rubber bands for train tracks.
Laughs. You're on the right track, though. They're a bit more sophisticated than that. But yeah, it's all about finding that balance between a secure hold and enough flexibility to handle that expansion and contraction.
So clever. It seems like they've thought of everything. But I'm guessing actually welding those rails together is a whole other challenge.
You said it. It takes specialized techniques for sure.
No kidding. It's not like you can just break out your dad's old arc welder from the garage.
Laughs. Probably not. The document mentions a few different methods, each with their pros and cons. There's flash butt welding, which uses electrical resistance to heat up and fuse the rails together.
Okay, so that one's definitely high voltage. What else?
Then there's electric arc welding, more versatile, but it can be a bit slower and messier. And then, for the pyromaniacs out there, there's thermite welding.
Thermite welding, that's the one I wanted to hear about. Okay, tell me everything.
Picture this. They've got these two rail ends, right, that they need to join together. They pack them with this mixture of metal powders, often aluminum and iron oxide, and then, boom, they ignite it.
No way. They actually blow it up.
Well, it's a controlled explosion, of course. But yeah, this mixture burns super hot, like thousands of degrees, hot enough to melt steel and fuse those rails together.
Wow, that's insane. Using fire to fight fire, or at least to fight the problem of not having continuous rails. But even with all this, the super strong steel, the thermite explosions, nothing lasts forever, right?
Yeah.
So what happens when a rail starts to wear down? What then?
Well, that's where things get really interesting.
So even with all this incredible tech, the thermite, the ultrasonic scans, you're still talking about metal grinding against metal day in and day out. There's got to be a ton of wear and tear.
Oh, absolutely. And it's unavoidable, really. But the first step in dealing with it is understanding what we're up against.
Okay, so break it down for me. What's wearing down the rails?
Well, we can talk about two main types of wear, vertical wear and lateral wear.
Vertical wear, so that's the top of the rail where the wheels make contact.
You got it. And as you might imagine, the faster and heavier the trains, the faster that wear happens. A freight train lumbering uphill. That's different from a high-speed train zipping along.
Right, totally. Different levels of wear and tear. What about this lateral wear, though?
That's all about the sideways forces, especially when you're talking about curves. The train leans into the turn, the wheels push against the rail, trying to, well, shove it outwards.
Ah, okay, I could picture that. So how do they keep the rails from literally being pushed out of alignment?
It's a combination of things, really. You need those strong rail fastenings, of course. But the design of the rail itself matters, too.
Ah, so this is where those different rail profiles come in again.
Exactly. A wider rail head, for example, can help distribute those lateral forces more evenly.
It's amazing how much thought goes into all of this. It all connects the material, the design, the type of train using the track.
Exactly. Every detail matters. But let's face it, even with the toughest steel, the best designs, nothing lasts forever. Eventually, those rails reach a point where it's just not cost-effective to keep repairing them.
Right, got to draw the line somewhere. So, how do they decide when a rail's time is up?
The document talks about something called optimum lifetime. Basically, it's about finding that sweet spot, getting the most out of a rail before you have to replace it.
Makes sense. A balance for performance and, I'm guessing, budget.
Exactly. They factor in the initial cost, obviously. But then you've got maintenance over the years, the potential risks and costs if a rail fails. Imagine a derailment. And then, of course, you have the benefits of newer, maybe more durable materials.
It's a whole cost-benefit analysis.
It really is. And there are so many variables, it's impossible to say, oh, a rail lasts X years, and that's it. But to give you a general idea, a rail on a super busy line, tons of traffic every day, that might last around 40 years, at least according to this document.
40 years, that's pretty impressive.
Right. But that same rail, if you put it on a quieter line, less wear and tear, it could easily last twice as long.
Wow, so it's like they get a second life, those rails.
They do. Railways are actually really good at recycling and repurposing. That's a whole other fascinating topic.
I bet. But, okay, so even with all that, eventually there comes a point where a rail is truly at the end of its line. Then what? Scrap metal heap.
Nope. They melt those old rails down and use that steel to make new rails. It's a very efficient cycle.
Talk about sustainable. This whole deep dive has really been eye-opening. I never realized how much there is to know about train rails. It's a whole hidden world.
It really is. It's engineering, it's materials science, it's even economics, all these things we don't usually think about when we see a train track.
Right. We just hop on the train and go, well, I know I'll never look at those rails the same way again.
That's the beauty of exploring these things, isn't it? You start to see the everyday world differently.
Absolutely. It's like those rails are hiding in plain sight. and they've got these incredible stories to tell. Well, on that note, I think we've reached the end of the line for this deep dive.
Indeed. But I hope our listeners will keep exploring, keep asking questions, keep marveling at the ingenuity that keeps our world on track.
Well said. And hey, the next time you're on a train, take a moment to look down at those rails. Think about the journey they've been on, from molten steel to tireless workhorses. It's pretty amazing when you think about it. And that's it for us this time. Until next time, keep those wheels turning and those minds engaged.